Hello. In this discussion, we're going to look into reading hexadecimal numbers. So computers count in base 2 or binary, and all numbers in a computer, and all data boils down to numbers, are stored in binary. So an example of chart showing numbers 0 through 15. And actually this chart shows 3 different number systems. Decimal on the left, and over there on the right is binary, which we'll look at next. And in the middle is something called hexadecimal. And since this discussion is called reading hexadecimal numbers, really our target is to understand the purpose of the middle column here, hexadecimal numbers. So reading through decimal numbers and counting up in them, that should be familiar to all of us. 0 through 9, of course. Since it's base 10, now we're out of unique digits. So we have the concept of place that we learned in elementary school in order to be able to express really an infinity of numbers with a set of 10 digits. We have the idea of place. So when you read 10, that's really in your mind. In elementary school, you thought this through explicitly. That's the tens place. So it's really 1 times 10. Right? And if I had a hundreds place, it would be 1 times 100, etc. So that in that way, we can use only 10 digits to represent an infinite set of numbers, if you're patient enough to write them all down. So let's look at the binary over on the right, and not as familiar with that, so we'll count through that. And again, binary is on and off switches, so the machine likes the on and off switches, and machines are easier and cheaper to develop that have just on and off switches. So that's why computers use binary. So we have 4 binary digits there. And that's what's necessary to count through 0 through 15. We needed 2 decimal digits to get to 15, but we need 4 binary digits because we only have 2 digits, so you need more positions to represent the same numbers. So we start counting at 0 and then read across the columns there. 0, 0, 0 is all represented the same way, and then 1 also is represented the same way as binary and in decimal. But then we run out of digits. So then we have the concept of the twos place. So when we add 1 to 1, we get 2, and we have to jump over to the twos place in binary to represent 2, and then 3, and then carry the 1 and go to the fours place. And so the last place is the eighths place. When we jump down to the 8th column, and you'll see that the fourth digit there is lit up there, and that's the 8th place. Okay, and then counting and so forth. So 15 combinations. Okay, so that's place values in decimal and place values in binary, and we did a little bit of counting of the binary. We'll come back to this table in a second. So hexadecimal has 16 digits. So that's the reason why this table is organized from 0 to 15. Okay? 16 digits. But because it has hexadecimal is 16 digits, it's base 2. It's base 16 is another name for it, hexadecimal. So base 16. So it has 16 individual numerals. So when we get to 10, we don't need to jump over to the place. It would be the 16th place, actually, over here, and the 32th place, and etc. over there if you wrote them in hexadecimal. But we have A to take place of the 10 in hexadecimal because we have another digit there, A, B, C, D, E, F. Now, computers don't count in hexadecimal, but they come up in computers all the time. And now that you see hexadecimal numbers is written this way, 0 through 9 is possible digits, then A through F, you're going to start to see them. It's like learning a new vocabulary word. You start seeing it all over the place. And you'll see it, especially as you learn to be a computer programmer. A lot of information that is presented to computer programmers is presented in hexadecimal format. That's why it's important to learn. Okay? Why do we use hexadecimal format? Do we just need to give students something else to learn? Well, it's because 16, hexadecimal is 16, right? So 16 digits. And 16 is the power of 2, precisely 2 to the 4th power. 4 digits, 2 to the 4th power. So binary numbers fit neatly inside of it. Look here, back on this chart, right? We didn't have this binary number here represented in decimal. We had to go over to another digit. And these digits aren't full up of combinations now, right? Full up of combinations would mean it goes to 99. Right? With this hexadecimal digit that went from 0 through 16 combinations neatly represents in its entirety this set of binary numbers, 4 of them exactly. Okay, so that 4, keep that 4 digits in mind. So a single byte is 8 binary digits, so it could be represented this way, say. So that 4 bytes there and 4 bytes there, also called the nibble actually by some people. But so in hex this is represented this way. right? So this can be written this way, and that's why we use hexadecimal to report numbers in computer programming. Sometimes it's convenient not to translate it into binary, but to leave it into something that can be read conveniently as binary. And hexadecimal is something that you get a little bit of practice, you can start to see the binary pattern that's underneath the hexadecimal digits because they map directly on them. Okay, so they're convenient to write. Instead of writing all these 8 digits, you just write 2. But you take a common 4-byte integer, right? You could take 30. That would take 32 binary digits to express. Now, say you have 100 binary digits and you want them all in binary. It gets verbose. So if you take 8 hex digits to express, and with a little bit of practice, your mind can map the hexadecimal right onto the binary. It's just a better way to communicate binary numbers among human beings, and that's the purpose of hexadecimal. Thank you.